Hello again, everyone. In this lecture, I want to continue into Survey Chapter 17, talking about this really important phenomenon of standing waves. So a couple of applications which you can see on this slide, which we're going to come back to. So this is Survey and Jewett, Chapter 17, Section 17.2 to 17.5. So as a bit of a motivation, every musical instrument, say a stringed instrument like a guitar, a violin, a harp, works by setting up a wave on a string. And that wave vibrates the air, and as we've talked about, that vibrations of the air vibrate your eardrum, which you hear as sound. So understanding which frequencies the strings can vibrate at explains the sounds that we hear when we listen to a violin or a harp or anything like this. To kind of illustrate that, let me play this nice little video. Okay, so all of these are slow motion, ultra slow motion videos of instruments being played by the Toronto Symphony Orchestra. You can see the waves vibrating on this string. So as she drags the bow across here, you'll see the waves appearing. Okay, so that's just a fun little application. If the quality is not good in the recording, I encourage you to open up the link and watch it yourself, because it's a really nice illustration of waves showing up when you play an instrument. A second application is that one we've talked about before. If you have a structure like a bridge, for example, and it oscillates at certain frequencies, you can create standing waves by jostling that structure at the right frequency. And one of these examples, which we talked about before, was the Tacoma Narrows Bridge, where the wind was jostling it, setting up a standing wave, and that eventually led the bridge to collapse. So that's something you need to pay attention to as an engineer. Finally, if you're interested in lasers, a laser is basically a standing wave of light, and so that's another application of why standing waves are important. So that's the kind of dessert first. Those are the kind of interesting applications. Now let's get into the details. This lecture, I want to talk about what a standing wave is and how to represent it in an equation. And then finally, we'll talk about which frequencies will lead to standing waves in a string which is fixed at both ends and a pipe which is open at one or both ends. And the application there is, of course, the musical instruments. A string which is fixed at both ends is like a violin, a harp, so on. A pipe which has one end open or both ends open is a wind instrument like a flute, a trumpet, so on. So to begin, let me remind you about the traveling waves that we've talked about so far, waves on a string. We said that each one of these little beads on this string was undergoing simple harmonic motion. If I watch this green one, it travels up and down with this amplitude, and that all of the beads on this string have the same amplitude. So if I watch a different green one, it's traveling in simple harmonic motion also, up and down. And the amplitude of that simple harmonic motion is the same as the amplitude of this green one or this red one. They all have the same amplitude. And when you think about energy, that means that each one of these beads, if I treat it like a simple harmonic oscillator, has the same energy, because the energy of a simple harmonic oscillator is 1/2 Ka squared. They all have the same amplitude. That means they all have the same energy. And if I want to get the total energy on the string, I just add up all of the energy of each one of these beads. The second thing I want to remind you of is we talked about how to add waves if they encounter each other. So if you have two waves on the same string moving to the left and to the right, let's say, for example, over here, we know that when they encounter each other, if I want to find out the net effect of those two waves, I take the displacement from wave 1 and the displacement from wave 2 and add those together, and that gives me the net displacement. We add them up point by point. That was called the superposition principle. So you can have waves adding up because their displacements are both positive, and then you add those two, you get a bigger positive number, and then they pass through each other. Or they can cancel each other out, which was the situation for destructive interference on the left here. If that's with one of the waves has a positive displacement at a certain position and the other one has a negative displacement. So now What I want to focus on to show you what a standing wave is, let's focus on two waves with equal amplitudes and equal frequencies, but traveling in opposite directions. So the waves are going to be identical. The only difference between them is one is going to be traveling to the left and one is going to be traveling to the right. And we want to add those two together to see what kind of thing results. So here's a little simulation. I've got a blue wave and a red wave. You can see they have the same amplitude and the same frequency, so the same period, same amplitude. And then this black line is the sum of those two. So at every point, I add together the value of the blue wave plus the red wave, and that gives me the black one. So you can see, like, at the origin here, the blue wave has a displacement of about pretty close to 0.5, and the red one has a displacement of exactly the negative of that, like minus 0.5. So if I add those two together, I get 0, which is why the black line is at 0 at this point. And here, those two are adding up. That's where I have the constructive interference. So this is a particular snapshot. Now let me put it in motion. One of the waves is going to move to the left, and one is going to move to the right. And you'll watch what happens to the black one as I add those two together at every time. Okay, so hopefully you are seeing this now. You're seeing the waves traveling slowly. The blue one is traveling to the left. The red one is traveling to the right. And I'm adding those two together to get the black one. If I look at the black one, I don't see any traveling at all. I see it kind of staying in place. You know, the crests are not moving to the left or to the right. The crests are staying in place. Like there is a kind of maximum at this point here, which isn't moving to the left or to the right. It's just staying there. And there are other places on the string where they're always at 0. So for example, here's one at 0.5. This little piece of string at x equals to 0.5 is always 0. It's never moving away from 0. So that piece of string is never moving, nor is the one at 0. Okay, so there are places where I'm getting, these crests are pretty big, large amplitude oscillations, and then there are places where there's no amplitude of oscillation. So at 0.5, at 1, and 1.5, those are not going anywhere. These places are called nodes. So that's the place where there's no motion whatsoever. And the place where you have the biggest motion is called an antinode. Okay. This is a standing wave. Standing because I don't see it traveling to the left or to the right. And what you can see is the standing wave is formed from two traveling waves in opposite directions, adding up. Okay, so just a simple question. When we saw that wave, that standing wave, we saw that there were these special points, the nodes, which were not moving at all. But there were also points which were having very big motion, which we call the antinodes. Now, when we talk about the traveling wave, we said that each of the little beads on the string had the same amplitude. So they all had the same energy. But then when I do the standing wave, there are points which don't move at all. So they have basically no kinetic energy, as far as I can tell. So just a simple question, when I think about, both of the waves had energy when I interfered them, and then after that interference, I end up with these points called nodes which don't move at all. Where did the energy go? Those don't have any energy at all. So where did that go? Here are some choices for you. Pause the video and see if you can come up with an answer to this question. Okay, so hopefully you have chosen one of these. Very simple question. Hopefully you realize that energy was destroyed is kind of a key word that should not be the case. You know that energy can't be created or destroyed by the conservation of energy. So definitely energy still has to be conserved. That's the point of this question. And then energy was lost to heat and friction. Well, okay, maybe, but what if there was no air resistance? What if I oscillated the string in a perfect vacuum and everything was ideal? Then there would be no energy loss. So the only sensible choice is that energy has to be somewhere else on the string. And if I go back to this simulation here, what you see is that, at this point at x equals to 0, the two waves are always destructively interfering with each other. So they have destructive interference at x equals 0 and x equals 0.5 and x equals 1. But there are other places where I'm always getting constructive interference. This point here at 0.75 and at 0.25, those places I have constructive interference. So the energy is like more than it was before for the two waves that constructively interfere, and less where it destructively interferes. So if I've got destructive interference somewhere, I've got to have constructive interference somewhere else. Total energy has to be conserved. So the nodes are places where you have destructive interference. They have less energy than the waves that they started with. The antinodes, which is where you have the big oscillations, are places where you have constructive interference. That's more energy than you started with. But the total energy is conserved, right? If I added up the total energy in that standing wave, it would be equal to the total energy in the two traveling waves. Okay, energy is conserved, energy is not created or destroyed. Okay, so let's try to describe this thing mathematically, this standing wave. So let's consider the case of those two sinusoidal waves, equal amplitudes, equal frequencies, traveling in opposite directions. That leads to a standing wave. That's what we saw from that simulation. If I think about the standing wave, if I look at a little piece of the standing wave, like look at this little piece of string, what's it going to do? It's going to oscillate up and down in simple harmonic motion. And this piece of string is also going to oscillate up and down in simple harmonic motion. So just like before, each piece of string oscillates up and down in simple harmonic motion. But unlike before, the amplitude depends on where you are. So remember, when I had the traveling wave, all of the pieces had the same amplitude. All of the little beads on the string had the same amplitude. Whereas for the standing wave, there are some places which have a big amplitude. We call those the antinodes. I have the biggest amplitude there. And then there are some places where I have zero amplitude. That's what we call the node. So the amplitude depends on where you are as a function of x, right? I still have simple harmonic motion, but the amplitude changes depending on which part of the string you're looking at. How do we come up with an equation mathematically for this? Start again with this trig identity. We've used this several times in this chapter. So the addition of two sine waves can be written as the product of a cosine and a sine, where the argument of the cosine is a minus b over 2, and the argument of the sine is a plus b over 2. So let's try and use this same identity in this case of two waves on a string with equal amplitudes and frequencies traveling in opposite directions, which should lead to a standing wave. So here I've got my first wave. That's traveling in the minus x direction. Remember, the sign here tells you whether it's traveling in the minus or plus x direction. So if it's plus, that means it's traveling in the minus x direction. And this one's traveling in the plus x direction. So the only difference between those two waves is that sign there. Okay, so this is exactly the form here. Addition of two sine waves. Let me call A the thing inside of the first sine wave and B the thing inside of the second sine wave. So what is A plus B? That's kx plus omega t plus kx minus omega t. So A plus B over 2 is going to be 2kx over 2. And so the thing inside of the sine will be kx. What is A minus B over 2? A minus B is going to be kx plus omega t minus kx minus another omega t. So it's going to be 2 omega t divided by 2. So when I use that formula, I get this equation down at the bottom. This is my equation for the standing wave. Let me call it y standing as a function of x and t. That's what I get if I add two traveling waves together, moving in opposite directions. Let's try to understand this a little bit more. So we said that the standing wave was, each piece was undergoing simple harmonic motion. Where's the simple harmonic motion? You can see it here, cosine omega t. That should remind you of the mass on the spring oscillating up and down. But the thing in front of the cosine omega t is what we call the amplitude, right? And in this case, the thing in front of the cosine is 2a sine kx. So it looks like the amplitude changes as a function of x, which is exactly what we saw here, right? So at this position x, I have a big amplitude. At this position x, I have a smaller amplitude. At this position x, I have zero amplitude. So the amplitude of the standing wave at a particular position x is given by 2a sine of kx. Okay? So the pieces of the string which are not oscillating are called nodes. and those are the places where the amplitude is 0. And the places with the highest amplitude are called the antinodes. That's where they have the biggest oscillations. Let me be clear. A is the amplitude of the two waves that I added together. So A is a constant. A is a constant. But the standing wave amplitude is not a constant. It depends on x, right? Because I have A sine kx. So I added two waves together. Each of the amplitudes of those two waves was A. And I get a wave which has an amplitude which depends on exactly where you are on the wave. Okay, where exactly are the nodes and the antinodes? Okay, so here's my equation for the standing wave. I want to know where those nodes are occurring. Well, the nodes have 0 amplitude. Their motion has 0 amplitude. They don't move at all. And so what that means is the amplitude of my motion, which is this thing here, has to be 0. Now, A is not 0. A is a constant. So that means I have to have sine of kx has to be equal to 0. The only way to have a place which has 0 amplitude motion is for somehow I have to have this whole thing equal to 0. And the only way that's possible is if the sine of kx is equal to 0. So that means kx is equal to n pi. N is some integer, 1, 2, 3, so on. Okay. Now you can write this in terms of the wavelength because k is 2 pi over lambda times x is equal to n pi. And then I can cancel out the pi's, and I get the position x is n lambda over 2. So that is this equation here. So where are the nodes happening? They're happening at x equals to 0, and then half a wavelength down the string, if n is equal to 1, and then 1 wavelength down the string, if n is equal to 2, and then 3 halves of a wavelength down the string, if n equals 3. You get the idea. Where are the antinodes? The antinodes are where the oscillation is the biggest. So that's where my amplitude out in front, this thing, is equal to plus or minus 2a. So in other words, my sine function has to be the biggest it can possibly be, which is plus or minus 1. So where does my antinode occur? It occurs when my sine is maximal. My node occurred where my sine was minimal, where it's equal to 0. When does that happen? It happens when the argument of the sine function is equal to pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2, so on, odd numbers, right? So if kx, the argument of the sine function, is an odd multiple of pi over 2, I will get the sine of kx equal to plus or minus 1, and I'll have the biggest amplitude motion that I could possibly have, which is what we call an antinode. You can combine these all into one formula. Once more, let me use, again, the relationship between k and lambda. I'll have 2 pi over lambda times x is equal to some odd multiple. M is an odd number times times pi over 2. And again, the pi's cancel. So I'm using m to denote something which is an odd number, 1, 3, 5, 7, so on. And you can rearrange this. You get x is equal to m lambda over 4, which is what I have down at the bottom there. Okay, so where do the antinodes occur? The first one occurs at 1/4 of the wavelength down the string. The second one occurs at 3/4 of a wavelength down the string, and so on. Okay, so these two formulas here tell you where along the string the nodes and the antinodes are. Just be careful. I'm using n to mean any integer, 0, 1, 2, or 3, and I'm using m to denote any odd integer, 1, 3, 5, or 7. Okay. Hopefully it's clear from the previous slide that the distance between the nodes is half a wavelength. Okay, so for example, x, let's say 2 here, is going to be equal to lambda. x1 is equal to lambda over 2. The distance between those two is lambda over 2. Right? And you can do the same thing with the antinodes. Let's say the position of the first antinode is lambda over 4. the position of the second antinode is 3 lambda over 4. The distance between those two, delta x, is lambda over 2. So the nodes are spaced by half a wavelength apart, and the antinodes are spaced half a wavelength apart. And the antinodes occur halfway between the nodes. So it's all summarized up here. The distance between the nodes is half a wavelength. The distance between the antinodes is also half a wavelength. And the nodes occur halfway between the antinodes and vice versa. So the distance between a node and the nearest antinode is 1/4 of a wavelength. For example, in this picture that's shown here, what's the wavelength? I'm drawing a particular snapshot of the string, is the green one that I just drew there. So be careful, only 1/2 of this kind of shape of the string in this photo is the actual string, right? This one here is at a different time. Okay, so I only pay attention to one side of this, this snapshot. So if I freeze time, the string will have the shape exactly what I drew there, right? And that has a wavelength of this far. Okay? So what's the different distance between the nodes? That's lambda over 2. Lambda over 2. And the distance between a node and an antinode, so let me write here, here's the node, node, and node. And then here's the antinode, here and here. Okay. So the distance between the node and the antinode is lambda over 4. And same thing here, lambda over 4. Okay. So just be careful. A lot of times students will get confused. They'll call like, this will be the wavelength, but that's not the case. I only look at one side of that string. If I took a snapshot, the string would have the shape of the green line which I drew there. So lambda is actually going from the first red dot to the third red dot in this picture. Okay. Let's do an example problem. 2 transverse sinusoidal waves combined in a medium are described by the wave functions shown. Determine, for part A, the maximum transverse position of an element of the medium at x equals 0.25 centimeters. So what have I done here? I'm adding 2 waves. They have the same amplitude. So this is A. They have the same wavelength, and they have the same frequency. Right? So they're identical waves, but there's a difference between them, which is that one of them is traveling in the positive x direction and one's traveling in the minus x direction. So this is a standing wave. We know that a standing wave is formed when you add 2 waves, identical waves traveling in opposite directions. Okay, what is this question asking? We know it's a standing wave, right? Of x and t is going to be equal to 2a sine of kx cosine of omega t. Okay. So the maximum transverse position of an element of the medium at x equals to 0.25 centimeters. So what does this mean, the maximum transverse position? That means the amplitude of this, what I'm calling the standing wave, a standing of x. So the amplitude of the simple harmonic motion of the little bead on the string at x equals to 0.25 centimeters. The amplitude of the standing wave, or the a standing, is 2a sine of kx. Okay, so this is what I'm trying to find here. So let's plug in the numbers. A standing of 0.25 centimeters is 2 times a, and a is 3 centimeters, times the sine of kx. K is the thing in front of x here. So K is pi, radians per centimeter. Whoops. Radians per centimeter. And then times x, I'm going to put in 0.25 centimeters. So what is this? This is 6 centimeters times the sine of pi over 4 radians. And the 1 over 4 came from 0.25, right? 0.25 is 1 over 4. So that's 6. I happen to know that the sine of pi over 4 is square root of 2, 1 over square root of 2 centimeters. 4.24 centimeters. So this is not a node, and it's not an antinode either. If it was an antinode, it would have an amplitude of 6 centimeters, the biggest it could possibly be. If it was a node, it would have an amplitude of 0. This is not a node or an antinode. Not a node or an antinode. Let's go to part B. What are the 3 smallest values of x corresponding to the antinodes? Okay, so once again, we know y standing is equal to 2a sine of kx cosine of omega t. The antinodes occur when this thing is maximum. Okay? Antinodes occur when sine of kx is equal to plus or minus 1. And so I must have kx is equal to pi over 2, 3 pi over 2, 5 pi over 2, so on. So this is what we had written before as kx is equal to m pi over 2, where m was an odd number, 1, 3, 5, 7, so on. Okay. So what are the first 3 values? X equals to m pi over 2k. And k is equal to pi, so it's m pi over 2 times pi radians per centimeter, which is m over 2 centimeters. So the first 3 are 0.5, that's m equals to 1 centimeters. 1.5, that's m equals to 3. And 2.5, that's m equals to 5. So those are my 3 positions at which I have my antinodes. Just to be clear, this first one was from m equals to 1, this was m equals to 3, this was m equals to 5. You can see that the spacing between those is 1.0 centimeters. And maybe it's worth thinking about what is the wavelength. Lambda is 2 pi over k, which is 2 pi over pi radians per centimeter, which is 2 centimeters. So you can see their spacing is 1 centimeter, which is half a wavelength, which is what we said. We said that the nodes are separated by half a wavelength. The antinodes are also separated by half a wavelength. So far we've talked about what a standing wave is. It's the addition of 2 traveling waves traveling in opposite directions. And we've talked about the equation for the standing wave, which was given here in the green box. And we're thinking of it as, each piece of the string or each piece of the standing wave is oscillating in simple harmonic motion, but the amplitude of that motion is given by 2a sine kx. So the amplitude depends on where you are. There are places with no amplitude. That's what we call the node. And there's a place where the amplitude is the biggest. That's what we call the antinode. The antinodes are spaced half a wavelength apart. The nodes are spaced half a wavelength apart. And the nodes occur halfway between the antinodes and vice versa. I'm going to pause here and leave this as a about 30-minute video. And then I will continue this in a second video just to make it a little bit more digestible. So I'll stop here and move on to the next part, which will be given in a separate video.